Welcome. This final lesson for the FBP system highlights the means for predicting the size and shape of a new fire as it grows from its initial location. This tool, as part of your initial fire assessment, allows you to predict the area burned and fire line perimeter in the first hours of the fire's spread. Further, it allows you to visualize the shape, even provide a rough drawing of it to aid in suppression decisions. As the image in the background shows, emerging fires develop a shape that is somewhat elongated, with the hottest fire burning at the head, least intensity at the back or tail, and intermediate intensity along the flanks of the fire. This elongated shape is similar to an ellipse. The specific shape of the fire ellipse will be related to the effective wind speed influencing it. As the fire image here points out, new fires grow from a point of ignition spreading more or less in the direction that the wind pushes it. At the same time, it grows laterally on the flanks and backing into the wind at its tail. The model that defines the elliptical fire shape is based on the effective wind speed, using that to determine a length to width ratio. The FBP system, using an open 10-meter surface wind, that would be observed at a fire weather station, estimates a length to width ratio based on the fuel type selected in earlier predictions. As the graph shows, there are distinct relationships for forested fuel types, slash fuel types, and grass, or open fuel types. Using the example wind speed of 12 miles per hour, you can quickly find the length to width ratio is 1.75 to 1 for forest types, meaning that it is nearly twice as long as it is wide. Considering an example in grass, the same wind speed of 12 miles per hour would produce a ratio of 4.4 to 1, meaning that the fire would be estimated as more than 4 times longer than it is wide. As shown here, observing and forecasting effective wind speed can be a very important skill. Remember that the effective wind speed is the combined effects of wind and slope. You can review these concepts in the lesson entitled Wind, Slope, and ISI. Using the estimated or forecasted effective wind speed, and knowing the fuel type the fire is burning through, the shape of the fire can be visualized and drawn on a map. You will notice that the open fuel beds, more exposed to surface winds, have longer and narrower shapes than closed fuel beds. For example, in the FBP system, a fire burning in a closed fuel type with a wind speed of 10 miles per hour has a length to width ratio of 2 to 1. The same wind on an open fuel type produces a 4 to 1 ratio and results in a much more elongated fire. Again, I encourage you to keep the fire assessment worksheet handy to reinforce the entire process. In this case, we will be documenting our results on the fire growth, size, shape section at the bottom of the worksheet. What do you need to estimate the size and shape of your fire as it grows during the first hours? First of all, you need to identify a time period over which you expect the fire will be burning. That time can be how long it takes you to arrive at the fire and allow you to estimate its size when you get there. It can be the time you estimate that the fire will continue to spread actively for the rest of the burn period, up to several hours. Knowing the time that is of interest to you, the spread rates estimated earlier can be used to calculate how far the fire is expected to spread in the direction the wind is blowing. This spread distance can be enough to help you evaluate what values are at risk during the burn period, how far the fire might spread in the time it takes you to escape to your safety zone, or how much time you have to complete your suppression action before the fire arrives. As mentioned earlier, you will want to keep in mind the effective wind speed you recorded earlier on the worksheet. In most of your fire behavior lessons to this point, backing fire has been an afterthought. But many times on the fire line, that is what you encounter and where you are most successful. The FBP system generally tends to produce higher backing spread rates than the US systems. It uses a separate backing ISI that can be compared to the ISI and used to predict spread rates and flame lengths itself. Again, you can review these concepts in the lesson entitled Wind, Slope, and ISI. Let's take an example situation. Assume that your assessment estimated the head fire spread rate at 9 chains per hour and the backing spread rate of 0.7 chains per hour. Further assume that you determined that at 1600 you estimate the fire will grow for another 4 hours today. You can add the two spread rates to produce a combined spread rate and then multiply it times 4 hours to get the spread distance of approximately 39 chains. Stop the video here and confirm the calculations for yourself. Now that you have an estimated spread distance, along with the estimated effective wind speed for your initiating fire, you can produce estimates of the area burned and the distance around the perimeter of the fire. The FPP system provides different estimates based on the sheltering from the wind. Closed fuel types include all deciduous, mixed wood, slash, and most conifer fuel types. Open fuel types include both open fuel types and C1, the spruce, lichen, woodland type. Tables 2.7 for sheltered fuel types and 2.8 for open fuel types offer both an area and a perimeter estimate. These two tables work in the same way. First, you find the nearest spread distance in the left column, and then find the effective wind speed at the top. You may use the eye level wind speed you observed on the fire line, but only if it was taken in the open. Where this row and column intersect in the area table, you will find the estimate of the acres burned. Let's try our example with a spread distance of 39 chains and an effective wind speed of 6 miles per hour. The resulting acreage is approximately 85 acres, using a little interpolation here. In much the same way, looking at the lower perimeter portion of the table, find the spread distance on the left and the effective wind speed at the top. Using the same example with 10 meters wind speed of 6 miles per hour and a spread distance of 39 chains, the intersecting row and column produce an estimated perimeter of approximately 107 chains. Remembering that there are 80 chains in a mile, we have estimated that the distance around the fire perimeter would be over 1.25 miles. People first learning this process find that these tables seem to defy logic. For any given spread distance, as the wind speed increases, the area and perimeter get smaller. We normally think that faster wind speeds will produce fire spread faster. In fact, they do. However, in these tables, we consider spread distance, not spread rate. A faster spreading fire will take a shorter time to go the same distance, and a faster spreading fire will produce a narrower, more elongated shape. We can see here in this example that the faster spreading fire with the same spread distance produces a much smaller fire. In conclusion, the process and tools outlined here are designed for new fires during the first burn period. They assume that early spread can be approximated by an elliptical shape. The inputs required flow smoothly from the spread rates estimated earlier. All you need is to remember the effective wind speed, estimate a time of interest, and produce a spread distance. The estimates of area, perimeter, and shape are crude but effective. As shown here, all things being equal, fires spread with the wind and are influenced by the fuels and barriers along the way. This tool can help you visualize that. Thank you.